We're going to start our lovely activity today that I've crafted. And yeah, hopefully you guys learned something. Hopefully it makes our section 7.1 makes a little more sense. We'll go with that. All right, so stupendous. Let's get started. I'm going to open up the first two questions here. They are both card sorting questions. Right. The first one, we have 4 vocabulary terms: sample, parameter, inference, and statistic. You need to match each term with its appropriate definition. All right, so that's the first screen. Match the term with its definition. Just stack them on top of each other. The next one is a scenario, and yes, I know there's a typo. That's what happens when they type too fast and don't double check and review. A business owner wants to know the average household income in her business's zip code. She randomly samples 80 households in the zip code and finds their mean income to be $46,144. I just realized I'm not sharing my screen, and that makes this a lot more difficult to follow at times. Sorry about that. Not that you guys can't see these on your own screen, but still. So we have, again, 4 terms that need to be matched up with their context. So we have statistic, parameter, population, and sample. And we have 4 contexts here from the example. Please match these to the proper term. All right, so we're going to go these next 2 problems. I'm going to give you 4 minutes. No, let's talk about these. If you finished, great. If you didn't finish, great. Let's talk about it. So on the first pair, or first set of cards to sort, where we're doing the definitions, we'll start with sample, because on my screen, if you're looking at my shared screen, is the first one on the left-hand top corner of my screen. So the definition of a sample, right? This is a subset of a larger population. Right? Parameter. Remember from yesterday, parameter goes with population. So a parameter is a number that describes some characteristic of the population. Inference is an estimation of a characteristic of a population using sample statistics. Right? You make an inference after you've collected all of your data. Right? You've done some sampling, and you use your data from that sample to make an estimation of what is actually going on. Right? That's an inference. And then a statistic, using the last possible combination, is a number that describes some characteristic of a sample. So again, statistic goes with sample. Is there anything I can clarify about the vocabulary terms? Then we shall move to the next set of things to pair up. And we have our business owner, want to know the income of the houses in her area. So she samples 80 houses and gets a mean income of $46,144. Right. So the statistic is X bar, the mean income of the sample. Right. So the statistic is based on the sample. In this case, it's the mean. It could be another type of value. For this example, they're interested in the mean. The parameter will be mu, the mean income of all households in the zip code. In this case, we don't have that value. We just know that mu would represent that value. Population. This is all households in the zip code. And the sample is a subset of that population, being the 80 surveyed households. All right. Is there anything I can clarify here? So again, please make sure you're moving through the slides here and answering the questions. This is part of the learning process. All right. So then we'll move on. It's there. So next. All right, so the next chunk we're going to do here will be the next 2 slides. And we're going to group them up into, well, no, sorry, I lied. We're just going to do the next slide. All right, so everyone should be shifting over to slide number 4 in this set of problems. This one has a fun little simulation we'll look at. So a sampling distribution is the distribution of statistics from all possible samples of the same size from a population. Note, sampling distributions are made of statistics. These could be means, proportions, quartiles, standard deviations, variances. Could be any number of things. All right. The statistic isn't always the mean. It could be the median. It could be a proportion of people who wear size 9 shoes. It could be, it depends on our variable that we're collecting data about. Right. So please keep that in mind. It's not always one certain type of value. Right. We have a sampling distribution simulation, which we'll look at in just a moment. This simulation estimates and plots the sampling distribution of various statistics. You specify the population distribution, sample size, and statistic. An animated sample from the population is shown, and the statistic is plotted. This can be repeated to estimate the sampling distribution. All right, so this will allow us to kind of see what the distribution, a sampling distribution, could look like. So it's kind of fun, kind of nifty. So first, you get the instructions. You're welcome to read those if you like. We're just going to jump into the sample. So we're going to hit begin. So we get this screen of stuff here. The top histogram is our parent population. So this is a representation of the parameter, so to say. In this case, we're looking at, we could do the mean, we could do the median, standard deviation, right? It gives us those 3 parameters. In this population, this is what the mean, median, standard deviation are. Right. I could change this to a skewed distribution if I want. I could make up my own. We're just going to go normal for now and work with that. All right, this next one is a sample distribution. Okay, this will show the distribution from the individuals in a sample that we collect. Right, so it's just from one sample. We can set, so right now this is set to collect the mean of a sample size of 5. So when I run this, it's going to select 5 individuals. That's my sample data. Right, and then this in the third histogram represents the mean of these 5 individuals. And we just have the one value because I only ran this simulation once. I can run it again. So this is the sample data for my second repetition, and I get now 2 data points in the sampling distribution for the mean. I could compare stuff, right? So this is a sample size of 5. The one below here, let's set this one to a sample size of 25. Right. And so we can run the sample. It'll do the 5, drop 1. Oops. I need to set that to the mean. Sorry, we'll try it again. This time it'll work. 3, 4, 5, and drop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, it's going to run through all 25 as a simulation. And drop our mean into the the fourth histogram here, right? And now we just ran one repetition comparing these. We're going to move this forward quite fast and just do 100,000 repetitions. So we'll do 100,000 samples of size 5 and 100,000 samples of size 25. Well, actually, let's just do 5 first. So not much to look at yet. Let's do 10,000. Now it's starting to normalize, right? So running many samples, right, gives us a lot more data, and we start to see a normal distribution emerge. If we go even more, not a whole lot changes. Right, but we can see, as we were looking at yesterday, that in a smaller sample size, we have more variance, right? In a larger sample size, we have less variance. Right, so those are things to remember. Right, and you're welcome to play around with this. I'll get this link into Canvas at some point today, so you can look in this and use it if you like. So that brings us back to this problem. What do you notice and what do you wonder? Please type that into the box here. And I'll give y'all 2 minutes. All right, I know that probably wasn't enough time to write everything you wanted to write. So while I'm talking, feel free to complete your writing what you were writing. Saw some really good noticings and wonderings in what you guys have here. Some of the wonderings will hopefully be answered as we work through this chapter. Something I do want to mention, so some of you guys were mentioning, like, what will the data look like as we get an even bigger sample size? And as we kind of discussed yesterday, as we do larger sample sizes, the variance should get less. So essentially, the histogram will get taller and narrower, right, as the sample size increases. But we do need to be careful not to violate the 10% condition. Our sample size should not exceed 10% of the entire population. Right? Otherwise, it starts acting funny. So as long as we're not violating the 10% condition, then we can just keep taking larger sample sizes if possible. And that should reduce the variance and give us a more reliable statistic. Yeah, there's some terms on there that I don't even know what they mean. Like, I don't know what kurtosis is. Obviously, it's a statistic thing. I can look it up. I can tell you guys, but I've not heard of it. Or if I did, it wasn't something I needed to remember for any class that I took. And then I'm trying to understand this question. It says, I wonder if the normal distribution of the mean, if it could somehow start decreasing without a sudden increase. I want to answer this question, but I'm not sure what it means. Okay. Okay, that's fine, Liliana. Thank you for checking in. All right. Anywho, excellent. A lot of these questions, hopefully, that you have the wonderings will be answered as we continue to work through the chapter. We're going to continue on and move it forward here. So I'm going to open up the next slide, but I'm going to keep this one available so you can go back to it if you want to look at any of these things. So please progress to the fifth one, sample or sampling. And I'm actually going to open up the one after that as well, just don't go there quite yet. So sample or sampling, the whole point is to say what these two things are and recognize that they're different. A sample distribution is not the same as a sampling distribution. And we have pictures of a population, sample, and sampling distribution. They're all related, right? The sample comes from the population and the sampling distribution is built off of samples. Right? So they're related and they're connected, but they're definitely not the same. So in this entry window here, you should be typing in what these things are, kind of like their definitions. So what is a sample distribution and what is a sampling distribution? In the next slide, accuracy versus precision, we wanted to discuss how do you avoid bias and how do you reduce variability. For these two questions, please only write one thing. I don't need a list of things. One way to avoid bias, one way to avoid or to reduce variability. You can't avoid variability. One way to reduce variability. And try to think in context of this chapter, right? We've discussed things about bias and variability in previous chapters, but think within the context of what we're trying to understand for this chapter. All right, so we're going to answer these two questions next. Excellent. All right, let's bring it back here. I know some of you guys are finishing up typing what you're typing, and that's totally okay. So first, let's go back to sample or sampling. Right, I saw a lot of good responses here on this one. Many of you guys are showing that you understand the idea and the difference between the two. We're going to give you guys some specific answers essentially, right? So a sample distribution, and I actually think someone said it very well. Yeah, so we have a good response here that I'm going to read. A sample distribution is the values of the variable for all the individuals, well, for all the individuals in a sample from the population. All right. So if we're looking at our pictures here, it's the second histogram. There's a sample distribution, right? The sample distribution is the whatever variable we're collecting data on. It could be a value, it could be a preference, right? But it's the responses from those individuals in the sample. The sampling distribution, right, is the values from all the possible samples of the same size from the population. Right, so it's collecting a single statistic from your samples to then put together in a bigger set of statistics, so to say. In the examples here, they're using means. All right, so the sample distribution recorded the income of the individuals in the sample. The sampling distribution then took the mean income from those from that sample and recorded it. Then they did another sample and took the mean and recorded it into the sampling distribution. So the sampling distribution is a collection of all the means of all the sampling, of all the samples. All right. So anything I can clarify? All right. Then we go to accuracy versus precision. All right, we can avoid bias by taking a random sample, all right, doing a simple random sample. We're using random sampling. However you want to word it, we need to sample randomly. That's the best way to avoid bias. Okay, and as far as reducing variability, have a larger sample size. That is the kind of an easier way to reduce variability, right? If I take a larger sample, then I'll have less variability. We've seen that in the simulation and we heard about it yesterday in the notes. So those are one answer for each of these. Avoid bias, random sample, reduce variability, larger sample. Put it in a nutshell there. Is there any questions? So then next, we're going to go to the next two questions. I'm going to go here. There. We're going to jump to screens 7 and 8. So everyone's going to move. All right. So hopefully you pause here on the first screen here, Arizona iced tea. The next two questions have the same directions, but you're looking at two different contexts. Each bold-faced number in the context below is the value of either a parameter for the population or a statistic from the sample. Choose which each number is and then select the appropriate notation to describe the number. Right, so for this one, we have on Tuesday, the bottles of Arizona iced tea filled in a plant were supposed to contain an average of 20 ounces of iced tea. Quality control inspectors sampled 50 bottles at random from the day's production. These bottles contained an average of 19.6 ounces of iced tea. So below you have 8 options. You need to select one checkbox that correctly pairs the parameter with its variable and value, then select one checkbox that correctly pairs the statistic with its variable and value. All right, so there's 4 checkboxes that say parameter next to it. You need to select one of those. And then there's 4 that say statistic, select one of those. And you'll do the same thing for the following problem with New York to Denver. Read the context and then correctly pair the parameter with its variable and value and statistic with its correct variable and value. Okay. And we'll take 3 minutes to do these, and then we will talk about it. The important thing here is to try. If you don't know, guess. Give yourself the opportunity to learn. All right. So I'll see, we'll talk about it here in like 3 minutes. Let me get my timer. Where's my 3-minute timer? There it is. All right, here we go, guys. We're going to bring it back to the Arizona iced tea question and correctly identify our parameter and statistic. All right, so we've got 20 ounces and 19.6 ounces. Those are our bold-faced numbers. Right. The 20 ounces is the parameter. All right, and that would be the mu or mean for the number of ounces in a bottle. So we want to find parameter equals mu. Our parameter is mu equaling 20 ounces. All right, the 19.6 is the sample mean, which would be x bar, and that's the statistic because the statistic goes with the sample. So we have statistic equals x bar, or x bar equals 19.6. Okay, so we're putting the vocabulary with notation at this point. We're trying to make sure we understand how those are connected. In the next problem, New York to Denver, we have 8% and 10% as our 2 values. The 8% refers to the sample proportion. That is a statistic, and that will be with the notation p hat because we're talking about a proportion, and so that's p, like p probability proportion, p hat, and that statistic p hat equals 0.08 or 8% of the sample. Parameter is 10% because the actual value, right, for the population should be 10%. So we have parameter equals p, or parameter p equals 0.10 or 10%. So those are the 2 correct checkboxes for this one. Right. So again, parameters don't have the special like extra notations on them. There's no bar or hat or anything. It's just like a Greek letter or just a regular letter. There's no specialty to the notation. Statistics get an extra little marking on them to show that it is a statistic. Right? Is there anything else I can clarify? Cool. So next, we're going to open up the next few screens. So I'm now shifting you guys to the last 3 screens. All right, it looks like I'm down to 18 people. All right. So here we go. We're going to take the next 5 minutes, all right, and read through these questions. I know it will not, 5 minutes will not be enough time to answer all these questions. All right, read them, think about how you can answer them. Think if you know how to answer them. If you do want to answer them, you can. That's fine. And then we'll talk about it. More importantly, read through the questions first. All right. Okie dokie. So once again, I know that was not enough time to answer all the questions or completely answer all the questions. Hopefully you did have the opportunity to look at each question and consider it. So I'm going to quickly go through these questions. Please follow along. So the first one, we have our orange M&Ms problem. All right. So Mars Incorporated says that the mix of colors in its M&M's milk chocolate candies is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. Assume that the company's claim is true. We want to examine the proportion of orange M&Ms in repeated random samples of 50 candies. Identify the individuals, the variable, and the parameter of interest. All right, so in this example, the individuals are the M&Ms. Right, those are the things that are part of our sample. Right, the variable is color. That's the thing that we're keeping track of the results. We're going to have our 50 candies, and each candy we're going to count how many are of each color. So color is the variable. The parameter of interest is the proportion of orange M&Ms. All right, so we would have p hat, right, for each of our samples. Right? And the p hat would refer to the number of, or the proportion of our sample that's orange. So any questions about this first one, the orange M&Ms first part? So in the next part, I know these graphs are small. I tried to make them bigger. I couldn't figure out how. So which of the graphs that follow could be the approximate sampling distribution of the statistic? The first graph here is a sample distribution. It is not a sampling distribution. This shows the results of one sample of 50 candies and how many candies were of each color. So the first bar graph here is not what we need. It's not the right type of thing. The next two are both sampling distributions recording p hat, or the proportion from each sample. Since we're assuming that the company's claim is true, the true value should be 20%. Of these two dot plots, the middle one here, the second one, has a mean or median that's right around 0.2. And I know it's hard to see. The second one has a mean or median that's around 0.4 and like nothing over 0.2. So that would not go along well with our data. So the correct graph would be the second one, showing a center of about 0.20. Is there any questions about this one? Lastly, we have our histograms of the values taken by 3 sample statistics in several hundred samples from the sample population. In the same population, the true value of the population parameter is marked on each histogram. So we have A, B, and C. The little arrow points to the true value. Which statistic has the largest bias? That would be histogram C. This is because it is obvious that the center of this histogram is to the left of the true value, meaning that it's biased. We did not come close to the true value. The statistic that has the lowest variability is histogram A. It's the most narrow, which means it has the least variability. And based on the performance of the 3 statistics in many samples, which is preferred as an estimate of the parameter, that again would be A. And that's because it is the one with the least variability and the least bias, right? And that's what we generally want to go for a good statistic. So that is the answer to that one. Okay, so we'll open that up. that is the end of the activity. I know that I went over the amount of time we normally like to do in class, but I want us to be able to get through these examples, and because I think it's important. So if there's any other questions that you have or anything you'd like me to clarify, please let me know. Feel free to stick around and ask for some clarifying questions. Other than that, we're done for today. I will see you next week on Tuesday. So have a lovely rest of your week, a wonderful weekend, and I will see you next week. Have a great day.